The background of the industrial plant is oleochemical production. The main raw material is palm oil. Firstly, palm oil undergo transesterification process to produce methyl ester. Then, methyl ester is fed to blood flow reactors in which it reacts with hydrogen to produce both fatty alcohol and methanol. The reaction takes place where the temperature is in range of 217 to 220 degrees Celsius and a pressure of 260 bar gauge. Copper zinc catalyst is used to increase the rate of reaction. Since the reaction is reversible, hydrogen gas is fed in excess to push the reaction forward. The product will be first distilled according to the carbon change. Then the distilled products along with the unreacted methyl ester are then sent to product upgrading to further produce fatty alcohol from the unreacted methyl ester.
Looking into the distillation process, the major equipment is the distillation column X7C003. The feed is mainly crude fatty alcohol, which consists of C16 and C18 carbon chain with the flow rate of 1295.9 kg per hour. C16 has a boiling point of 240 degrees Celsius under the pressure of 0.014 bar, while C18 has a higher boiling point than C16 that can be separated using the distillation column under the operating temperatures of 250 degrees Celsius and 40 bar pressure. C16 with boiling point lower than 250 degrees Celsius will be discharged as top product, whereas C18 will be discharged as bottom product. In this case, the light key component is C16 and the heavy key component is C18. The bottom stream S9 will be recycled back to the reboiler to be fed into the distillation column together with the crude fatty alcohol feed and high pressure steam. In the distillation column, the variable that we desire to control is the operating temperature of the distillation column. To keep the temperature as control variable, we manipulate the flow rate of the high pressure steam. The disturbance variable in this system are the ambient temperature, recycled stream S8 temperature, as well as the inlet S1 temperature.
The original control system for this process is a feedback control, where a temperature transmitter is used to detect the temperature of the bottom stream S5 and convert it to electrical signals. The signals are then sent to a temperature controller to adjust the temperature to the desired set point value by manipulating the flow rate of the high pressure steam through the valve V3. This is the process control that we propose to this system. It is a feed-forward control where the disturbance variable, the inlet stream temperature S1, is measured to control the system. A temperature transmitter is used to detect the temperature at S1 and convert it to electrical signals. The signals are then sent to a temperature controller to adjust the temperature for S2 by manipulating the high pressure steam flow rate through the valve V6. However, this control system is considered unpractical as the other disturbance variables such as the temperature in stream A, recycled C18 stream, and ambient temperature could not be controlled. Hence, the original feedback control is relatively a better choice for this system. It is a very simple control system where it measures the output temperature and makes necessary changes accordingly. Most importantly, it is effective for all disturbance. The control system produces a reliable and repeatable performance by reducing the system's sensitivity and giving faster time response. Lastly, it also helps in increasing the stability.
Referring to the PFD, this unit is a buffer tank receiving fatty alcohol from the distillation column as seen from stream 8. Basically, the buffer tank operates at the atmospheric pressure with a temperature range of 180 to 190 degrees Celsius. The product of the tank, as shown in stream 9, is pumped from the receiver to the reactor using a positive displacement pump. In conjunction to that, the objective of the buffer tank in the proposed process design is to stabilize the flow rate of the product before entering the reactor. The original control system of this major equipment is the cascade control, where the controller driving the set point, in this case the level controller of the buffer tank, is called the master controller. Moving on, the controller receiving the set point, in this case the inlet flow rate controller of the buffer tank, is called the slave controller. However, the cascade control is not performing well in the system because of its complex tuning process. In addition to that, level controlling is not suitable in this system because the positive displacement pump will build up pressure in the tank when valve V1 closes. Therefore, a simpler and more cost-effective control system was proposed to control the level of the buffer tank for an optimum operation. In this system, the controlled variable is the level of the buffer tank. The manipulated variable is the outlet flow rate, whereas the disturbance variable is the inlet flow rate of the buffer tank. The proposed idea was to change the cascade control to two feedback control by connecting the level indicator controller to the fourth valve respectively. That way, the level can be controlled by just adjusting the recycle stream flow rate, while the inlet flow rate to the reactor remains unaffected. The proposed design is practical and possesses an advantage because the cost of the two feedback control system is lower as compared to the cascade control system. This is because the cascade control system uses more control equipment than the two feedback control system that is an equivalent single loop system. With the use of more control equipment, the cascade control is expected to have lower reliability due to the error of each equipment. Although some argue that the slightly lower reliability is not an issue to the use of the respective system, but it is always best to minimize the possibility of error to occur in the process control system. Henceforth, to maintain the feedback control system when the slave sensor or controller is not functioning for the proposed design, the dual feedback control system has a flexibility to bypass the secondary sensor or controller and have the primary output directly connected to the valve.
After the C18 fatty alcohol flowing out from the buffer tank, the product undergoes through upgrading process. As shown in the PFD, the major equipment in this process is the reactor X11 RO1, where hydrogenation of the unreacted methyl ester takes place. C18 fatty alcohol from X11 DO1 flows into reactor X11 RO1 through stream 10, where it is pumped by a positive displacement pump E4 at an entering flow rate of 38,000 kg per hour. The unreacted C18 methyl ester is reacted with excess hydrogen gas. In the reactor, unreacted C18 methyl ester will reduce from 250 ppm to lesser than 20 ppm. The operating temperature and pressure of the reactor is at the range of 217 degrees Celsius to 220 degrees Celsius and the 260 bar gauge respectively. Then, the high purity C18 fatty alcohol flow out from the reactor with the flow rate of 38,100 kg per hour and temperature at 235 degrees Celsius. There are few transmitters to measure, which are pressure, temperature, and level. The main objective in this process is to control water level in the reactor. This is due to pump dry run could occur if the water level is too low, and it could lead to process upset as well as pump damage. Therefore, the control variable has to be water level of the reactor. The water level can be controlled by either inlet or outlet flow rate of the reactor. However, inlet stream is dependent on the upstream process. It is not controllable in this process, whereas outlet flow rate can be controlled without affecting the upstream process. Hence, manipulated variable is the outlet flow rate of product, and disturbance variable is in this process is inlet flow rate of the reactant. Since manipulated variable is adjusted in order to meet the control variable, this is a feedback control system. To propose a new control system, there are three types of controls available, which are feed-forward, feedback-feed-forward, and cascade control. If we were to have a forward control system in this system, the disturbance variable where the inlet flow rate has to be controlled by controlling the inlet valve V1. If we were to have a feedback feed-forward control in this system, both the level controller and flow controller are connected to control the valve V8. If we were to have cascade control, a flow transmitter and flow controller are needed to add at the outlet of the reactor. Then, a cascade relationship can be formed by connecting the LIC14 controller to the new flow controller. The advantage of having feed-forward in the control is that the level of the system could be very stable. However, it is not practical as controlling the inlet flow might upset the upstream process. Therefore, it is not practical. The advantage of having feedback feed-forward control is to reduce the effect of disturbance and compensate the inaccuracy in the process model. However, as previously mentioned, it is still impractical to implement feed-forward control in the system. Therefore, feedback feed-forward is not suitable. Having cascade control would give faster response towards the change of set point. However, this will be an overkill as the objective of this control is just to maintain the reactor level in such a way to prevent dry run to occur. Besides that, the level control itself is able to satisfy the process control, and a very accurate level control is not necessary because in the end, the level control is there just to prevent pump from drying run. Moreover, cascade control is an expensive technology. It might not be economically feasible when it's implemented. Therefore, it is not recommended to implement cascade control as well. As a conclusion, the best recommendation for the control system in this process is to maintain feedback control system.